Differential forms are these expressions like y squared dx, r dr d theta, and so on. So things involving these d terms, these d expressions. So in this video, I'll try to explain how these actually work and what they actually mean. This is a little beyond the scope of this course, so it's all right if this doesn't completely make sense, but it can be very helpful for understanding and to help rederive formulas. So I'll talk about first, what are they? What are they? Then differential forms versus vector fields. Since in what we've been doing so far, we've kind of been treating these as the same. I'll also say what vector fields are. And then talk about area forms, so how we get that this formula is equal to dx dy, and then also work through a detailed example using these, which I think will help clarify what's going on. Okay, so first of all, so a zero form is just a function of however many variables. So like f, x, y, z. A one form is an expression like negative y squared x dx, or x dy minus y squared z dz, or so on. A two form could be something like dx dy minus 3z squared dx dz. So the number is just how many d expressions you have. So a two form has two of these multiplied, and then so on. So we can differentiate a zero form or a function to get a one form. So the one form df is del f by del x dx plus del f by del y dy plus del f by del z dz. So this is essentially the gradient of f, just by a different name. So dx kind of corresponds to I, dy kind of corresponds to j, and dz kind of corresponds to k. I'll be a little more specific about this in a second. But what do these, like what do dx and dy and dz, what do these actually mean? So a slightly more precise definition is, so a one form is a linear function from tangent vectors to the real numbers. So why do I say a tangent vector? So let's say we imagine this curve in two-dimensional space. So the tangent vector here is, it's not a very good, okay. Tangent vector here is this, and the tangent vector here is this. So let's say this is something like 2i plus j, and this is also 2i plus j. This plausibly looks like it could be that vector. But if we take a function, our one form, even though these are the same vector, it could treat these differently because they're at different points. So if our one form is, I guess, yeah, dx is the one form that will send I to 1 and j to 0. And so when I say linear here, that also means that like dx of ai plus bj will be a dx of I plus b dx of j is just a. So if this was, no, let's say this is 0, 0, and this is 2, -1 in the plane. And I had, and my one form was omega equals -y dx, then here omega of 2i plus j would be 0. But here omega, so omega at 2, -1 is dx. So then here omega would send 2i plus j to 2. So if we draw a grid, so Cartesian grid, then I'm going to write del by del x for the tangent vector which is I everywhere. So here, this would be del by del x. Here, this would be del by del x, and so on. Whereas df is the operation dot with I. And then similarly, del by del y would be the tangent vector j everywhere. Whereas, oh, sorry, this should have said dx is dot with I and dy is dot with j. Whereas if we take del by del r, now this will depend on, so let me draw this in a different color, I guess. This will depend on where we draw this. So del by del r would be, this vector would just be del by del x at 1, 0. But here it would be this vector. Here it would be this vector. Here it would be this vector. And then similarly, del by del theta would be this vector here, this vector here, this vector here, like this vector here, this vector here, and so on. So to some degree, del x and del by del x and del by del x and dx both sort of correspond to just the unit vector I. The reason for distinguishing them is that they play different roles. So what we did with, remember what we did with gradient vectors. So if we had a tangent vector u, and we had the gradient of f. So nabla f or df, what we did is to form the directional derivative. So duf is u dot or del f. And then this is at some point. So like x0, y0, z0. So this is why I'm thinking of like this as a vector, but this as an operation. So something blank dot a vector. More specifically, these behave differently under a change of coordinates. So like if you have two vectors, let's say u dot v is equal to 4. Now maybe your coordinate system is like this. Now you change your vector, your coordinate system to be like this. So now in the new coordinate system, u will be twice what it was before, which would mean that this dot product would get multiplied by 2. And well, v would also get changed. But if this number 4 is something like intrinsically meaningful, not just like you want to sort of get the same answer in every coordinate system, then you would have to divide v by 2 in order to still get the same answer. So another way to say this is we think, so if you've seen some linear algebra, we think of del by del x as the column vector 1, 0, 0, whereas dx we think of as a row vector 1, 0, 0. In physics, sometimes they use the terminology, they'd call this a vector, but then this they would call a covector. So to reiterate, dx will send like a del by del x plus b del by dy to a, and dy will send a del by dx plus b del by dy to b. So it is sort of just the I and j that we're used to, but this is a more a coordinate-free way of saying this. So I'll do an example in a second, but first I want to talk about area forms. Okay, so to multiply two forms, there's a couple of rules. So we get a negative sign anytime we swap the order of two things. So dy dx is negative dx dy. Then for something like dx dy dz, so we could swap, if we swap the first two, this will be negative dy dx dz. If we swap the other two, this will be negative dx dz dy. This we can swap again, will be dy dz dx. And now we need to have, so these are all equal, and then we could get, this is dz dx dy, and this is negative dz dy dx. So of these 6 possibilities, there's only, of these 6 orders, there's actually only 2 different possibilities. So 3 of them will be equal to each other, and the other 3 will be equal but with the opposite sign. Okay, so this might seem strange given what we've said about you can integrate in either order, so I'll explain that in a second. So then the second thing is, well, this is really a corollary of the first rule, but dx times dx, well, if we swap the order, that would be negative dx times dx, but of course that's the same thing we had to begin with. So 2 dx is 0, and so dx is 0. So any one form times itself is 0. Here I guess I've just said this for dx, but this sort of follows for any one form. Okay, so to apply this to the area, so remember our area differential, which is a 2 form, is dx dy. Now our formulas in polar coordinates are x equals r cos theta and y equals r sine theta. So dx is going to be cos theta dr minus r sine theta d theta, and dy is sine theta dr plus r cos theta d theta. And so dx dy will be cos theta sine theta dr minus r sine squared theta d theta dr plus cos theta, I guess r cos squared theta dr d theta minus r squared sine theta cos theta d theta d theta. But then these cancel out since dr and d theta are 0. And then this term is the same as plus r sine squared dr d theta. So we get that dx dy is equal to r cos squared theta plus sine squared theta dr d theta, or is just r dr d theta. So this is how we can derive the area differential in polar coordinates without going through some explicit geometric argument where we draw like these circular slices and take some limit. Another way of thinking about this calculation is so the fact that that dx, or the fact that these things cancel, that when you take something with itself, it gets 0, and when you swap the order, you get the negative. You can work out that this means that you can also calculate this by taking a determinant. So what did we say? Dx was cos theta dr minus r sine theta d theta. So minus r sine theta d theta, and dy was sine theta dr plus r cos theta d theta. So if we take this determinant, then this gives us r cos squared theta dr d theta, and then we're taking minus minus in the other direction. Oh, I'm sorry. So these two should be swapped. So we should have negative r sine theta d theta and sine theta dr here. So then this will give us plus r sine squared theta dr d theta. So the first column is dx and the second column is dy. Okay, so why doesn't this contradict what we've seen about, like we've said, integral f x y dx, dx dy equals integral f x y dy dx. So why are we saying that dy dx is negative if we didn't have a negative sign for this integration formula? Well, the kind of integration we've developed for two-dimensional integrals is actually a different kind of integral than we had for one-dimensional integrals. Remember, in one dimension, we didn't just integrate over an integral ab. Instead, we integrated from a to b of fx dx. And if we integrated from b to a, so assuming let's a is less than b, less than equal b, then in one-dimensional calculus, we did define this to be, these two to be negatives of each other. So you're not just integrating over an interval from a to b, you're integrating over an oriented integral, or oriented interval. So integrating this is different. Specifically, it's the negative of integrating like this. And so that's what's going on here. We haven't really talked about orientation. Let me just write the word. Orientation is sort of what's going on here. So we haven't talked about orientations in two dimensions, but that's what's happening, is if we were taking an oriented integrals, then that's why we would get this negative sign. And this will come up in the next unit. All right, now how about that example? So let's take f of xy is equal to y over x. So in polar coordinates, f of r theta is equal to tan theta. Now, if we calculate df in Cartesian coordinates, then this will give us negative y over x squared dx plus 1 over x dy, or that's 1 over x squared negative y dx plus x dy. Whereas in polar coordinates, df will be sec squared theta d theta. So to compare these, first remember, I'll do this in a separate color. So we always have cos squared theta plus sine squared theta is equal to 1. And so if we divide, that will give us 1 plus tan squared theta equals sec squared theta. Now, tan theta is y over x, so this is 1 plus y squared over x squared, which is x squared plus y squared over x squared. So df, now we're sort of mixing two different coordinate systems, but is x squared plus y squared over x squared d theta. So to reconcile these two answers, we need to show that this is equal to this. So negative y dx plus x dy is x squared plus y squared d theta. So for this, so we'll start out from tan theta equals y over x. Then we'll sort of do implicit differentiation here. So we'll get sec squared theta d theta equals negative 1 over x squared dx, or negative y over x squared dx plus 1 over x dy equals 1 over x squared negative y dx plus x dy. And from what we just saw, this is equal to x squared plus y squared over x squared. So we get that d theta is d theta is negative y dx plus x dy all over x squared plus y squared. Now, what's interesting here is that despite the notation, d theta is not d of a function or d of a zero form. And this is basically because the function theta, if you tried to define theta of, this is not well defined. Well, first of all, it's not defined at 0, 0. You can't meaningfully assign an angle to that, but it's also not continuous. Maybe I should say not of a differentiable zero form. So theta is not continuous, basically because 0 degrees is 360 degrees, is 720 degrees, and so on. So if you go around a circle, it'll sort of jump from like 359 degrees if your theta is going like this, or your x and y are traveling in a circle, your theta value will go from 359 degrees to 0 degrees, which isn't continuous. However, this sort of phenomenon where multiple numbers can represent the same angles doesn't happen when you start talking about the change of an angle. So even though 0 degrees equals 360 degrees, you were talking about like a wheel that was rotating, 0 degrees per second is not equal to 360 degrees per second. It's not the same as 720 degrees per second. Here, there's no motion, it's standing still. Here, this is 1 revolution per second. Here, this is 2 revolutions per second. Okay, so maybe I'll, and this is sort of, I guess, related to my research, or is sort of a starting point for that. Let me just finish by saying one more time. So the reason why we distinguish between, so d theta is del theta by del x dx plus del theta by del y dy. And we don't really have a direct formula for theta in terms of x and y, which is why we went through this sort of implicit differentiation way of getting at that formula. Whereas whereas d or del by del theta is del by del theta is del x by del theta, del by del x plus del y by del theta, del by del y. So now, like, these are the opposite things. So then del x by del theta, this would be negative r sine theta del by del x, and this would be plus r cos theta del by del y. So del by del theta is negative y del by del x plus x del by del y, but we don't have this denominator here. So this is what I meant when I said the d's versus the del by dels behave differently under changes of coordinates.